Example 3.4. Determine the ACI design moment capacity VMN of the beam shown if FC prime is 4,000 psi and Fy is 60,000 psi. We have this section. It has an overall depth of 18 inches, effective depth of 15 inches, it has width of 10 inches, and it has a steel area with 3 pieces of number 9 bars equivalent to 3 square inches. The first step here is to check the steel percentage. Okay? Before we can compute the VMN, we have to check the steel percentage so that we will know if it is within the permissible values in the code. Okay? So for the actual steel ratio, we have to compare it with the maximum and the minimum. Okay? So it should be lesser than or equal to the maximum, and it should be greater than or equal to the minimum. Now for this problem, I will use table A.7 to determine the minimum and maximum. Remember, our FC prime is 4,000 psi and our Fy is 60,000 psi. So let's look at this table and determine the values of the maximum and minimum. So here we have 4,000 psi and we have 60,000 psi, and the intersection of the two is this. And for the minimum, the raw minimum for flexure is here, 0.0033, and the maximum, it happens when the strain in the steel or the tension strain is 0.005. So the maximum is here. So this will be your maximum and this will be your minimum. Okay? So going back here, the minimum is 0.0033 and the maximum is 0.0181. Okay? And all we have to do is to calculate for the actual. And the actual steel ratio can be calculated as this, using this formula. We are given AS, we are also given B and D, and just plugging in the values and calculating, we can generate the actual to be 0.020. Now, is this value greater than the minimum? Yes. So this is satisfactory in terms of minimum. For the maximum, 0.181, is this lesser than the maximum? No. Okay? But they are very close. So you should not conclude right away that this is not permitted in the code, because the two values here are very close. And there is a gray area between compression controlled and tension controlled. That is the transition controlled. If we look at this graph here, we have here the x-axis to be the strain in tension or steel, and this one is the strength reduction factor. Now we have three zones here for the strain. We have the compression controlled, which is here. We have the tension controlled, which is here. And we have this gray area here, transition between tension controlled and compression controlled. Now this compression controlled is totally not permitted to be designed for beams, because it will make the beams brittle, and brittleness in the beam will promote a not ductile behavior, and we want the beam to be very ductile, because if the beams are not ductile, then if there are chances when the loads are so much that it makes the section a failure in terms of strength, if the beam is compression controlled, it will just crumble down and collapse. Whereas if it is tension controlled, it will have some symptoms so that the occupants of the building can evacuate before the collapse happens. And those symptoms are deflection, cracking, or vibration. So therefore, a ductile beam is an ideal beam design. So this one is the only zone permitted by the code. Alright? So permitted by the code is when the tension in steel is 0.005 or 0.004. But this one will have a different treatment in terms of its strength reduction factor. Okay, now going back to the problem. First, we calculate for the value of A, because our goal here is to solve for the tension strain in steel. Okay, so let's compute for A. We know that C equals T, and C is 0.85 FC prime AB, and T is AS FY. So that we can solve for A, and that is equal to AS FY over 0.85 FC prime AB. Hence this formula. So plugging in all the values which are given man, so we can have this answer. And beta 1 is given as a formula in the code. This is the formula. Beta 1 is 0.85 minus FC prime over minus FC prime minus 4,000 over 1,000 times 0.05, and it should be greater than or equal to 0.65. But here our FC prime is already 4,000. So 4,000 minus 4,000, that is 0. So automatically our beta 1 is also 0.85, because this value here is automatically 0. Okay, so we have our beta 1. Therefore, we can already compute for the value of C, because we know that C is A over beta 1. Okay, or A is beta 1 C. And then manipulating so that we can solve for C, C is A over beta 1. Hence, we get this value. Then after that, we are now ready to solve for the tension strain in steel. Let me illustrate that one using this graph of the strain. The strain in concrete is always 0.003. And the strain in steel, we don't know. But we know C, and C has a value of 6.22. This one is given in the problem. This is 18 inches. And this one is 18 minus 6.22. So we can solve for the tension in steel using ratio and proportion. Tension in steel, this one, the base over the height, that will be 18 minus 6.22, and that's equal to this one, 0.003 over 6.22. And we can get the tension in steel, the tension strain. Using your calculator, you can solve it, and this is 0.00423. Okay? So, 0.00423 is greater than 0.004. Going back here. So, it is within the zone, but is less than 0.005. Okay? So, therefore, this is in the transition zone. Okay, 0.004 and 0.005. This is your upper limit. And this one is your lower limit. And our actual tension in steel is 0.00423. So, this is less than 0.005 but greater than 0.004. And it is in the transition zone. Okay? So, because it is in the transition zone, we have to calculate for the phi. Because if it is in the tension zone, tension controlled, automatically the value is 0.9. If it is in compression zone, automatically the value is 0.65. Since it is in the transition zone, we have to use ratio and proportion, or we can simply calculate using this formula. Okay? So we will use this formula. And then we just have to transfer it here. So you can trace it where it's coming from. Okay, here. This is just ratio and proportion, by the way, of this triangular or a sloping line. Okay? So to cut it short, this is the formula. So we have 0.65 plus 0.00423. Okay, this is the tension in steel minus 0.002 times 250 over 3. So your phi now is 0.836. That is your phi. Okay? So we are now ready to calculate for the Mn. Mn is simply T times the moment arm. The moment arm is D minus A over 2. And T is obviously AS Fy. So plugging in all the values, we have calculated A, D is given, Fy is given, and AS is also given. So calculating all of this, we can get 185.3 foot kip. Okay? And then for the ultimate strength, we introduce the phi that we have calculated here. Plug in the phi, the phi here. And then multiply it by 185.3 and you will get this value. Okay? Thank you very much.